Cool. Okay, so last class we covered two things after the general review. We talked about a method for defining the boundaries for a strata. This was the cumulative square root of the frequency approach. Okay, so we worked through an illustration of how that method would work. And again, basically the idea here is we can use this cumulative square root, which essentially just means taking the sample sizes for each of the different known bounds and then using those sample sizes to determine where we should cut or bound our strata, depending on a pre-selected number of strata. The second thing that we started talking about, and this is what we left off working through last class, was the idea of stratifying after sampling. So as a refresher, when we stratify, we split our population into different groups or regions. Ideally, those regions are going to be as similar within as possible and as different between as possible, which is in some sense the same idea as, well, what you would expect to see if you have different groups, like say in an ANOVA situation. With stratifying after sampling, we have already collected a simple random sample, and we are now correcting the estimates that we retrieve from that simple random sample using the known population weights. So the idea itself is pretty straightforward, and we can show that the actual method for computing, for example, the average value after we have, or via post-stratification, follows the same formula that it did in the regular stratification case. Again, the difference here is just that these mu hat h, these value here, they come from a simple random sample. Sorry, I'm trying different pen thicknesses today. Okay. So these mu hat h in this context comes from a simple random sample. So we've collected the SRS and then we've split the SRS into groups based off of the characteristic by which we are stratifying. So we're going to look at an example of the application of this momentarily. As you can expect, this application will be very similar to what we saw in the general stratification case. So we'll find an estimate for some population quantity and then we'll bound that estimate. In order to bound the estimate, we need to work out a formula for the variance of the estimator. So last class, we started by working at the expected value of our estimator. And we showed that this expected value, as you would probably expect, is unbiased. Okay, so under post-stratification, if we want to estimate the mean, we know that the expected value of that estimate will be equal to the true value. This is ideal because now we just have to find, or whatever estimate has the smallest variance would be the best estimate for a given problem. Okay, so to work out the variance, we're going to utilize the rules that we defined on the previous slide. So we'll start off by making a note of these rules. Okay, so we have to find the variance of mu tilde post. We need the following rule. Okay. So we know that the variance of some random variable x is equal to the expected value of that random variable squared minus the expected value of that random variable all squared. From the previous slides, so we had shown, for example, on slide 42, that the expected value of x can also be written as the expected value of x given y. So effectively what we're going to do here is we're going to apply this rule in the context of the variance rule that we're familiar with. So we can write that the variance here is equal to the expected value of the expected value of x squared given y equals little y minus the expected value of the expected value of x given y equals little y. And then these should be, well, we'll just keep it like this, squared. Okay. So this is a direct application of the rule or the definition that we established on slide 42, just being applied in the context of these values. All right, now what we can do is we can show that this thing breaks up as follows. So this becomes the expected value. Well, I shouldn't say this breaks up, but we can write this expression in a similar way by adding and subtracting a zero term. Okay, so we have the expected value of x squared given y. And then we're going to add in this zero term here. So this is minus the expected value of y of x given y equals y squared. Oh, and then, sorry, we're just going to take this bracket here. This part there, like this. Okay. Should use different colors for the brackets, I think. And then we have plus the expected value of x given y equals y squared minus the expected value of x given y equals little y all squared. Okay. All right, so we can now show, so we're going to call this part here the first part, and we'll call this term here the second part. Okay, okay, so part one is the this first part we can show is the expected value of the variance of x given y is equal to little y. Okay. And then part two is the variance of the expected value of x given y is equal to little y. So that means that the variance of x is equal to the expected value of the variance of x given y equals little y plus the variance of the expected value of x given y equals little y. Okay, so both of the results here, so the result for part 1 and for part 2, those both actually follow directly from the original expression for the variance. So for example, if we look closely at part 1, starting from, well, let's start at the very beginning. So in general, we know that the variance of x is equal to the expected value of x squared minus the expected value of x all squared. If we look at part 1, you can see inside here, and I'll just mark these brackets in red so you can see what I mean by inside. So you can see inside the outer expected value, you have the expected value of x squared given y minus the expected value of x given y squared. So this is the same form as the original expression for the variance. So that's why we can write part 1 as the expected value of the variance of x given y. Okay, so this rule inside the red brackets here, this is exactly the rule or the definition of variance that we established at the start of the proof and we know from our previous studies. Part 2 is a similar idea. Effectively here, if you were to take the expected value on the outside, so say for example, we ignored these inner brackets here. I'll put them back in a second, but just for illustration. So say, for example, you ignored these inner points here. Now you have the expected value of x squared. Oh, wait, actually, we can't do that. All right. So you can see, sorry, starting out again. If we look at the second term, you can see that we have the expected value of the expected value of a term squared minus the expected value of the expected value of that term all squared. So that's the same form again as the original proof. And that's why we can write that this thing is the variance of the expected value of x given y squared. All right, so now that we have established this part, we actually have to do, we have to apply this in the context of our derivation for the post-stratification estimate. Just going to try and get myself a little more room here. Yeah. So in part 1, okay, so this condition is saying the value of x squared given y. So the second term is saying the value of x given y all squared. These, right? Yeah, exactly. And the y is going to be a constant, like something known. So that's only going to be taken into account when you compute x. Okay. All right. Okay, so now what we're going to do is we're going to take this idea and apply it within the context or to find our post-stratification estimate. All right, so let's write to derive the variance of mu tilde post let n1 tilde equal n1 to nh tilde equal nh. Okay, so the idea here is in the context of our derivation, we're going to condition on the sample size. So as you might recall from the previous class, we had two random variables when we computed mu. We had mu tilde h and we had little nh. So in this case, just like we did in the expected value case, we're going to condition on the little nh being known. So that'll kind of serve that'll be like the y in the context of the general expression. Okay. So since the expected value of mu tilde given n1 to nh is equal to mu, we can write that the variance of the expected value of mu tilde post given n1 to nh is equal to the variance of mu, which is equal to 0. Right. Correct. Oh yeah, the question there, if you guys didn't hear it, was so mu is a constant, and that's why the variance of mu is equal to 0, and that's true. So the variance of any constant is 0. Okay. All right. So now what we can do is we can say from SRS, the variance of mu tilde post given n1 to nh is equal to the sum from little h equals 1 to capital H of WH squared 1 over NH minus 1 over capital N H times sigma H squared. Okay. All right, so the expected value of the variance of mu tilde post given n1 to nh is equal to the sum from h equals 1 to capital H of WH squared multiplied by the expected value of 1 over little nh tilde minus 1 over capital N little nh times sigma h squared. Okay. So therefore, are you tired, Chow? Okay, so therefore we can write that an estimate of the variance of mu tilde post is equal to the sum from h equals 1 to h of w h squared 1 over n1 plus, or 1 over nh plus 1 over capital NH multiplied by sigma hat squared. Okay. All right, and what we can actually see from the result here is that this is the same thing as what we had in the general stratification case anyways. So the forms are pretty much identical. Okay, so this will be our estimate for the variation of mu-tilde posts. Again, what we can see is that we're taking into account the sample size or the size of the strata from the SRS, but then we are correcting using capital WH, which is the true strata proportions. And just like before, what we can do with the variation is we can take the square root of it, which gives us a standard error. We can multiply by some coefficient like 1.96, for example, and then we can bound our estimate using a confidence interval. Okay, so for an example of that, let's suppose that a simple random sample was used to determine the average height of students at McEwen. Okay, so we are told beforehand, or we are under the assumption that the proportion of the genders are roughly equal. So we're assuming here that we're going to stratify by gender, right? So we can see from the samples collected that we have a total sample size of 100, but the proportion of male and females in the SRS are not, they don't align with our pre-established idea of the equal genders, right? So we would expect there to be roughly 50% of the sample being female and 50% of the sample being male. Instead, we have more of a 75-25 split. So in this situation, given that we have some knowledge that the gender should be equal, we can apply the post-stratification approach to correct, in some sense, this estimate. Okay, so in part A, we're being asked to construct a reasonable estimate from mu given the information above. So again, the idea here, we collected this SRS, we observed this roughly 75-25% split of the genders, but our pre-established information tells us that the gender should be roughly equal. So we are using post-stratification to correct these estimates. Okay, so the way that post-stratification works is that we take the true strata proportions and we use those to adjust the estimates from our split of this simple random sample. So we're told the gender should be roughly equal, which means that, so since genders are roughly equal, we should have W1 equals W2 equals 0.5. Okay. So notice in this case that we don't actually require the population count. So those capital W's represent the proportion of observations that should belong to each of the strata. In our formula, we can replace capital WH with capital NH over capital N. But again, this is simply a fraction that represents the proportion of observations within each of the strata. So if we have that proportion, we can go directly to the calculation. So following from this, we can say that our estimate mu hat post is going to be the sum from little h equals 1 to capital H of WH squared multiplied by mu hat H, which is 0.5 times 142.2 plus 0.5 times 200.66, which is 171.43. All right. And then we're asked to compute the standard deviation of this bound, or the average of this, or the estimate of the standard deviation of this estimate, I should say. All right, so here we would have the variance of mu tilde post is equal to the sum from little h equals 1 to capital H of WH squared 1 over little nh plus 1 over capital NH. In hindsight, H was a bad choice for strata because n's and h's look way too similar. Multiplied by sigma squared h. Okay, so this is going to give us 0.5 squared, 1 over 76, plus, okay. So we don't actually have capital N here, so we're going to make a little bit of an adjustment to help us out. So assume capital N is very large given it is unknown. Maybe an oversimplification, but we don't really have a choice in this particular context. And then we will have times 4.3 squared plus 0.5 squared, 1 over 24 times 7.32 squared. This gives us 0.0137, 0614. All right, and then we can say that the standard error of mu tilde post is equal to the square root of 0.01370614, which is equal to 0.117. Okay. All right, so that's an example of applying our post-stratification estimate. As you can see, the general computation itself is pretty straightforward. It pretty much mimics exactly what we did in the stratified case. You have to hit the lights. It's okay. It's okay. Okay. So it pretty much mimics exactly what we did in the stratification case. The only difference here again is that we're taking into account the observed sample sizes from the SRS that we collected beforehand. All right, so there's one other topic in the stratified lecture that I want to talk about, which is the topic of double sampling. Double sampling essentially refers to the idea of stratifying and then stratifying again. All right, so let's suppose that we don't know the stratum sizes capital N little h. Okay, but we still want to stratify based on some population characteristic. So how can we do this? Well, one thing that we can do is we can utilize what is called double sampling. So in double sampling, we have a large sample that's used to find the allocation proportions. And then from that sample, we split based off of those proportions essentially. Okay, so the idea is to use a sample to estimate those strata proportions. Okay, so let n prime represent the phase 1 sample or the large sample that we collect from the population of interest. Then we'll let little h or little a subscript h prime, which is little n prime subscript h over little n prime, be the allocation proportions for the strata. Okay, so this is basically an estimate of WH. Okay. So here we have note that A prime H is unbiased for the estimator of AH, which just means that it's unbiased for the stratum proportion. Okay, same idea there. From A prime H, we can allocate the observations into N prime and into their corresponding strata. Then we collect simple random samples of size NH from each of the strata. So that's where the double sampling part comes in. Okay, so if we use double sampling, we have the following properties. So our estimate of mu tilde based off of, or our estimate of mu based off of the double sampling approach is basically just the estimate from each of the SRSs that we collect from the strata multiplied by those approximated strata weights. And then our variance estimation is given below, where we have n prime divided by n prime minus 1 times the sum of AH prime minus AH over N prime multiplied by the variance in each of the strata divided by NH plus AH prime mu H minus mu prime ST squared over N prime. So our variance computation is a little bit more cumbersome, but we can see here that at least if we have A prime H over N prime being close to 0, we get some reduction, but we can also see that what's happening here is we're basically just taking into account the estimates of the strata weights, and we're utilizing those to bound our estimate for mu. Okay, so I'm going to walk you through an example now of how the post-stratification approach is going to work. So the idea here in this last illustration is just to describe what would happen under double sampling, just to give you an idea of how this could evolve. Okay, so there's a data set in R called the faithful data set, and it contains two variables. One is the elapsed time between eruptions, and one is the duration of the eruptions of 272 eruptions of Old Faithful Geyser. So basically, it's how long the geyser was erupting for. So there's 272 measurements. Each measurement has one variable attached to it, that is how long the geyser was actually erupting. The other variable is how long you have to wait to see the geyser erupt. All right, so we want to estimate the average waiting time with a bound on the error of estimation. So to do this, we're going to set up the sample in the following way. We're basically going to stratify based off of two different groups in the data set. All right, so to try and explain this, all right, so given the shape of the waiting time variable, is bimodal with a split at 70 minutes. Okay, so we can actually visualize the data set, which is where this information is coming from. So this first part is just kind of setting up how I'm going to split the population. Okay, so we know that this is a bimodal distribution with a split at 70. So what I mean there is if we were to sketch the curve, we would have something that looks like this. Okay. So this is the waiting time. And then this mark here would be 70. Okay, we want to estimate average waiting time. So our goal, let me actually just make this not a colon. So the goal is to estimate average waiting time. The issue is we do not know how many observations are below 70 minutes and how many are above. Okay, so this is the general issue that we run into in the double, or when we would utilize double sampling. So we want to estimate this value. We know that there is, like say in the variable of interest, there's a clear separator. So there's something that splits it into two different regions. So in this case, it's this marker of 70. So below 70, you have sort of one set of data, and then above 70, you have another set. So we might consider those to be different strata or different groups. The issue is we don't know how many values are below and how many are above. So we want to estimate this proportion. Okay, so to do this, we can declare the following. Okay, so let n1 prime be number of observations below 70. Let n2 prime be number of observations above 70. Okay, so step one, collect a sample of size n prime from the capital N equals 272 values. Okay. Then two, count number of values below 70 minutes and number above 70 minutes. Okay, so that's basically the first step of the double sampling approach. So we have this large population of 272 observations in this case. We have this split point, which is the values below 70 in waiting time and the values above 70 in waiting time. And on the first step of this like double sampling approach, maybe I'll call this 1A and 1B just so that we don't get it confused with step 1 and step 2 as in double sampling step 1, double sampling step 2. Okay, so on the first step, we collect a sample of size n prime. Okay, so we're just collecting a simple random sample from the 272 observations, say of size 200. Okay. And then we count the number of values below 70 and the number above. And then we can use those to approximate the little h prime, or to approximate the WH, I should say. Okay, so suppose little m prime equals 200, then n1 prime equals 124, and n2 prime is equal to 76. Okay, just artificial values. These aren't coming from any place in particular. I'm just kind of making them up to illustrate how the approach would work. Okay, so this would then give us the following. So that means that A1 prime is equal to 124 over 200, which is 0.62. And A2 prime is equal to 76 over 200, which is equal to 0.38. Right. Okay, so now what we would do, and of course I've, as per usual, made a mess of the slide here. Okay, so now what we would do is we would collect samples from the N1 prime and from the N2 prime. All right. Sorry, one second. Okay, so step one, we collect our sample of size n prime. We're going to say that that n prime sample was a size of 200. Then we use the n prime sample to find the number of observations that adhere to each of our strata boundary, which in this case is the waiting time cutoff. So we have n1 is equal, or we have n is equal to 200. Sorry, this should be n prime. So we have n prime is equal to 200. And that would give us n prime 1, which is equal to 124, and n prime 2, which is equal to 76, for example. So then we can use these to compute estimates of the strata weight. Okay, and then what we do, following from what was described beforehand, all right. So from the 124 observations, we would collect a sample of size N1, and then from the 76 observations, we would collect a sample of size N2. You have a question? Is this, yeah, so capital N is 272 and N prime is 200. So N prime is the size of, say, the simple random sample that was taken from the population. Okay. All right. So then collect a sample of size N1 from N1 prime and a sample of size 2 from N2 prime. And then once we have our sample of blah, 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 blah. Once we have our two sample sizes, so N1 and N2, then we can construct estimates for mu1 and mu2, and then we can basically build our estimate for the overall waiting time, and then we can bound that estimate using the variation formula given on the previous slide. Okay, so everything from that point on is exactly like we have seen before. The only thing that's different in this case is how we actually set the problem up. So in this situation, setting up the problem basically means taking an SRS, using the SRS to find the strata boundaries or to find the strata proportions, and then sampling from within each of those samples that we collected to find the AH, to then create an estimate for mu, and then find an estimate for the variance so that we can bound that estimate. All right, any questions on that idea? Okay, so the next topic then is ratio and regression estimation. So I'll just set that up now with the time that I have remaining. So this is the next lecture set, which is lecture set 4. In this lecture set, we're going to be returning to the ideas of simple random sampling and stratified sampling. But within the realm of simple random sampling and stratified sampling, what we're going to do is take into account auxiliary information that could help us in our estimation of the variable that is of interest. Okay, so the idea here is this, or the goal of this unit is the same as the goal of the previous units. So we have some variable that we want to estimate. Well, we have a population quantity that we want to estimate for some variable of interest. In addition to having information about the variable that is of interest to us, we might also have information about an auxiliary or a subsidiary variable. So what I mean by that is, suppose that you collected a simple random sample and you wanted to measure the height of people. Okay, so you have an SRS of size 100 and you have the heights of all of the people in your SRS. But you also have, for example, the weights. We know that height and weight are correlated with each other. So in our pursuit of estimating, say, the average weight of this population of interest, we can utilize in our pursuit to estimate the average height of the population of interest, we can utilize the weights in our sample to improve our estimate. And that's what ratio and regression estimation are about. So they are methods for incorporating this auxiliary information into our estimation scheme. Okay, so there are different situations where we can use this, and we are going to look at the two situations based off the sampling schemes we have seen before. So we are going to utilize ratio and regression estimation within the context of simple random sampling and within the context of stratified random sampling. Okay. So again, we can use ratio estimation when we're interested in estimating a population parameter, but we are, for example, missing information, or we can use ratio estimation when we are interested in estimating some population parameter, and we have this auxiliary variable that can improve our estimate. In some situations, we might be directly interested in estimating the population ratio itself. So in this case, we would define the population ratio theta as being the ratio of the mean of y, which is the variable of interest, over the mean of x, which is the auxiliary variable. Okay, so if we wanted to estimate, for example, the total for y, we can show that through ratio estimation. We can do this without actually knowing the population value. So in the first general situation shown above, I mentioned that we can use this to estimate a population parameter without having crucial information. Okay, so for example here, right, we want to estimate tau without capital N. Okay, so that's what this example was referring to. So we know that the estimate for tau is capital N times the estimate for mu. Through ratio estimation, we can build an estimate of the total for the variable of interest without knowing capital N. And we can see how that would work below. So we have tau y over tau x. Okay, sorry, I'll finish this up. Variable of interest. This is auxiliary variable. And we can see that when we use the ratio of the two, the capital N's cancel out. So ratio estimation is providing us with a strategy to include correlated information, which can improve estimation. And it also gives us the ability to perform estimation for a parameter if we are missing key information, like, for example, capital N. Okay, so we're going to go through the usual process. We're going to start by deriving the properties of the estimates, which we'll do on Friday, and then we'll see some examples of how this would work. So as always, if you guys have any questions, please let me know. A reminder that the second quiz is on Monday. If you need any kind of accommodation, please email me as soon as possible. And the third assignment is due on March 12th, I believe. So there's still a few weeks before that's due. Otherwise, I will talk to you guys on Friday morning.